I think it's time for us to talk about some astronomy news. And we actually got kind of a doozy today. This one's very cool. So I'm going to preface this by saying I am not an expert in this particular subject. Extragalactic astronomy and cosmology are both not really my thing. I'm going to do my best to explain this as best I can, but there is a non-zero chance that some of these things might be wrong, so I apologize ahead of time. If I come up with any corrections, I'll address them next time or something. Vast bubble of galaxies discovered, given Hawaiian name. I don't know why they really needed this part. We do a lot of that, actually. A lot of stuff that we identify in space is given Hawaiian names. On the modern stuff, I should say. Obviously, a lot of it is old Roman, Greek, and sometimes Latin. But a lot of modern stuff we use Hawaiian, especially extragalactic stuff. Part of the reason for that is that a lot of the stuff that we do is because of the telescopes in Hawaii. Exactly, Nexi. It's a big part of the culture of modern day astronomy to sort of give back in a little bit of a way to the location that allows us to do these types of observations. Kind of neat if you ask me. Let's actually read the article and then we're going to jump to the paper itself. So, University of Hawaii led discovery of an immense bubble 820 million light years from Earth is believed to be a fossil-like remnant of the birth of the universe. To make a long story short, because it gets pretty dense from here on out, effectively what we're looking at, if we take the very early universe, pretty soon after the Big Bang, this was at the point where the universe was so hot and dense that photons couldn't really exchange easily. They would just run into things, kind of like they were escaping the sun. I gave the astronomy fact a while ago that a photon escaping the sun can take thousands to 100,000 of years to escape from the center to the outside of the sun. Similar concept here. Everything was so dense and hot that photons just couldn't really travel. So a lot of the interactions that we had in the very early universe were less about light and more about gravity and also pressure. In the very, very early universe, we had this really hot, dense plasma. And a lot of the interactions that would happen would cause ripples in this hot, dense plasma. Think of it almost like gelatin, right? You smack one side of gelatin, the other side wiggles. Similar to that, but obviously the speed of sound matters on the scales like this. If we're talking 1,000 light years, and we're talking about the speed of sound through plasma, that's relatively slow. In the very early universe, what we would have is we would have these locations of high energy, which would cause ripples, pressure waves, to expand out from those points, right? Now, mind you, this is a 2D representation. We're talking 3 dimensions here, so instead of rings, we're talking about shells, little spherical shells. We should be able to observe these types of things, which we call baryon acoustic oscillations. I'll break that word down in a second, or that series of words down in a second. If we had a whole bunch of these points where we had very extra hot, dense plasma, all emitting their own sort of shock waves, we would get something that looks sort of like this, where throughout the universe we would end up seeing these rings of galaxies that would form as a result of these higher density of baryonic matter. Let's talk about this entire phrase here, baryonic acoustic oscillations. Acoustic means sound, we're talking pressure waves in the medium. Oscillation just means it's oscillating, so you have periods of high pressure, periods of low pressure. The real important word here is baryon. A baryon is effectively a catch-all term for all of the real matter in the universe. So we talked a lot about dark matter on Space Saturday. Baryons are just all of the real matter, whereas dark matter is non-baryonic, right? So baryons are including protons, neutrons, electrons, quarks. All of that's baryonic matter. Effectively, what this term means is we have acoustic, pressure-based oscillations, changes in baryonic matter, baryon acoustic oscillations. And we know these things should exist, but we haven't really observed them, per se. I'm pretty sure. I don't know for sure, but I know that this is a big deal that we've found one for a few different reasons. And I think one of those reasons is that it is one of the first ones we've actually seen. And we found one by accident. The paper, if we actually look at it, actually just says it straight up. It's very funny to me. We were not looking for these. They weren't looking for any of these, and they found one anyway. These researchers were not looking for these. They found them, and they said, that's really cool. Let's check that out. And then they wrote a paper on it, which is awesome. This is like the most pure form of science you can possibly get, and I love it. So let's break this down a little bit. If we scroll down here, we can see sort of the first indication that something was up. So they were looking at this big survey, right? A whole bunch of galaxies at a certain Z, a redshift, a distance. And what they found was just by looking at it visually, and you can see it here, there's sort of this circle of denser points of galaxies, right? So every single dot on this top pane here is a galaxy. And they found that there were these sections where there were more galaxies compared to the rest, right? Compared to the background field. And you can see it visually. You can see it sort of like right here, this curve. That part's easy enough to see. And they actually outlined it in the red circle down here as well. So this was possibly one of these BAOs, one of these big shock waves that created, in this case, it looks like a ring because we're looking in 2 dimensions, but this spherical shell. If we were to actually look at sort of the radius, if we were to take radial shells, right, starting at the center, which is this red cross right here, if we were to take each of those sort of radii and bin all of the numbers of galaxies in a certain like thin ring, then we would get this histogram. This one's normalized up here in the top right, which means effectively we're saying how many more are there compared to the background. And you can see this big spike, which is represented by this red circle. So on this red circle in a sort of big sweeping circle, right? So it's got a thickness to it. It's like almost like an onion ring. The number of galaxies included is far beyond the average, right? We have so many more in here than usual. So there's some structure here. But now here comes the interesting part. Because this is where a lot of people who are learning science or have a passing understanding of it, or like pop sci people, this is where they stop. And they're like, hey, look, there's a thing there. We're done. In this case, these guys being scientists, they knew that this spike could be anything, right? Having a circle where there's more stuff doesn't necessarily mean that you found this theoretical structure, this BAO sphere, right? So they had to find out, hey, is this data actually showing me what I think it is? Or is it just a trick of the structure? Is there some other science going on here? Is there some other physics going on here? Or is it just random chance that we as humans are looking at and saying, there's a pattern, when in reality there isn't? We do that all the time. A great example of that, this image from eons ago, it feels at least, of a face on Mars. This is not a face. It's just a bunch of rocks that look like a face. And humans are really, really good or bad at seeing things and making patterns out of them. We see this and we immediately say, oh, that's gotta be a face. But when we actually sent a rover out there, it's just a bunch of rocks that were catching the light in a weird way. So that happens all the time, and we effectively wanted to make sure that that's not what was happening. How did they figure out if this peak was or was not a real thing? Well, they did a few different things. I'm gonna go over a few of them, well, really just one of them, and talk about that. So what they did was they said, all right, we know that there's a peak here, but we don't exactly know if that peak is what we think it is. Do we know for sure that these pressure oscillations would have caused this sphere to form, or in this case, this ring to form? Or is it just a random ring? So what they did was they ran simulations. They ran simulations of galaxy distributions, both in terms of just homogeneous distributions, so that means there's no structure to it, and then they ran a whole bunch, including the physics of BAOs. They took that curve from before, and they fit a line using the calculations without BAOs, and then they fit a line using the calculations with BAOs. And I think we can all agree that this blue line, which is no BAO, does not match the data, whereas this red curve, which says, yes, we do have a BAO, matches pretty dang well. That's still not good enough, because this could still be something else. This could just be random chance that looks like a BAO. So how do we figure it out from there? I mean, like, this is pretty good evidence, but it's still not perfect. So what they did was they ran the simulations like I was saying before, and they came out with a few different types of distributions. This red set of histograms and this blue set of histograms show 2 different scenarios that they tried without BAOs. Each of these 2 different scenarios are showing effectively the difference from what they would expect without a BAO. Right? So the lower, the more conformed it is. So they ran a whole bunch of these random distributions, and they found that both of these distributions are far below this dotted line. This dotted line is the parameters, the fit parameters from the actual object that they were looking at. What they call, I'm not going to try to say, actually maybe I will. Ho'oleilana, I think is how you would say that. I could be wrong. Any native Hawaiian speakers in the room, I apologize. I love the language, but I don't know it. We have these 2 different histograms. Neither of those histograms line up with what we actually saw, which means that this dotted line, which represents the feature that we're looking at, it's pretty likely that it's not random chance. It's pretty dang likely based on this, which was comparing random distributions to what we saw, and this fit to some BAO physics, mean that the actual structure we're seeing is actually a result of this BAO, and that's really cool. So this effectively says, hey, we found a thing, and they actually went a step further. This is what it looks like in 3 dimensions. All of the red dots are the points that we saw in their research paper. So this is, I believe this is the cross-section that we're looking at. I could be wrong though. So this is one view of it. And then another view. This is the same data, just a little bit different of a presentation. I like them both quite a lot. But I also want to point out that this one shows something else that's really cool. In the center of this, we have a thing called the Boötes supercluster, which is all of these black dots in the center. Now, when we have a BAO, right, what we would expect is that we have a whole bunch of stuff in the center that was clumped up really heavily that would cause this pressure wave in the first place. Since all of the dark matter, the non-baryonic matter, wouldn't be affected by that outshock, we would expect a huge gravitational well in the center of this entire sphere. So effectively, we would expect one big peak of galaxies and then a ring of galaxies around it. And this object, this giant structure, is all centered around this internal supercluster of galaxies. So it lines up beautifully with exactly what we would expect. Now this, of course, in its own is fascinating. But the real cool part about this is what it implies for cosmology. Here they do a whole bunch of cosmological fits, which I'm not going to get into, mainly because I don't know them too well. But what we see is that if we look at what is called the Hubble constant in quotes for this particular reason, we can see that their data, which is this black data point here, right, with its error bars, lays completely out of the range of this red line, which is what we would expect from a lambda CDM universe, which is effectively saying cold dark matter and dark energy included. Effectively what this means for us, to make it very short, is that this data, or I should say this datum, implies that the expansion rate of the universe for things closer to us is much higher than expected. Now, mind you, they in no point in this paper say that we believe this is evidence for that. This paper is simply, hey, we found this thing, and here's what our data shows us. They're not trying to make new physics here. They're saying, hey, if our data is correct, this could imply further physics of universal expansion in the later universe, so things closer to us, which is very interesting. But nonetheless, it's very interesting, and could open the door for some new interesting stuff. But I think, honestly, just the fact that we found one of these, and so stunningly too, like so obviously, like if we look at some of their data, right, like it's perfect. It lines up exactly with the estimations and with the calculations. It's beautiful. So